Somewhere above Earth, roughly 60,000 kilometers into the cold silence of space, a spacecraft is drifting. It is not spinning out of control in the dramatic Hollywood sense. There are no explosions, no alarms echoing through a control room. It is quieter than that, and somehow more unsettling. The European Space Agency's Proba 3 Coronagraph has simply gone dark. Its solar panels are no longer facing the sun. Its battery is dying, and the scientists who built it, who spent years dreaming about what it could show us, are now doing something they never imagined they would have to do so soon. They are waiting and hoping. To understand why this matters, you need to understand what Proba 3 actually is, because it is unlike almost anything humanity has ever sent into orbit. Most space missions involve a single spacecraft doing a single job. Proba 3 is different. It is two spacecraft working together in perfect choreographed unison, two satellites flying in formation separated by approximately 150 meters, executing a dance so precise that the margin for error is measured in millimeters. One satellite is called the Coronagraph, the other is the Occulter, and together they were designed to do something extraordinary: create an artificial solar eclipse on demand in the vacuum of space. Here on Earth, total solar eclipses are rare and fleeting. When the moon slides perfectly in front of the sun, blocking its blinding disk, astronomers get just a few minutes to study the solar corona, the sun's outermost atmosphere, a vast, shimmering halo of superheated plasma that extends millions of kilometers into space. The corona is one of the greatest unsolved mysteries in all of astrophysics. Its temperatures can reach over 1,000,000 degrees Celsius, far hotter than the sun's surface below it, and scientists still do not fully understand why. It is the origin point of solar winds that buffet our planet, the birthplace of coronal mass ejections that can knock out power grids and satellites. Understanding the corona is not just a matter of scientific curiosity, it has real consequences for life on Earth. But chasing eclipses from the ground is impractical. You are at the mercy of geography and weather, and even when everything aligns perfectly, you only get minutes of observation time before the moon moves on and the sun blazes back into view. For decades, astronomers dreamed of a better way. What if you could create an eclipse whenever you wanted, for as long as you needed? What if, instead of waiting for the moon to cooperate, you built your own occultation system and sent it into space? That is precisely what Proba 3 was designed to do. The Occulter spacecraft carries a large disk that, when positioned correctly, blocks the sun's bright face from the perspective of the coronagraph. The coronagraph, trailing 150 meters behind, can then photograph and study the corona without being blinded by the star it is trying to observe. It sounds conceptually simple. In practice, it's an engineering achievement so demanding that many considered it impossible just a decade ago. The two satellites must maintain their relative positions with extraordinary accuracy, adjusting constantly to account for orbital mechanics, gravitational variations, and the subtle pressure of sunlight itself. One small miscalculation and the eclipse effect collapses entirely. Since its launch in December 2024, Proba 3 had been exceeding expectations. The mission completed more than 60 successful formation flying orbits, each one a testament to years of engineering work and mission planning. Scientists were gathering hours of science data per orbit. The corona was being revealed in unprecedented detail. Teams at ESA's Mission Control were watching history unfold, orbit by orbit, as the sun gave up secrets it had kept for billions of years. Everything was working. Everything was on track. And then, in early February 2025, something went wrong. The exact nature of the anomaly is still under investigation, but its consequences cascaded quickly. Something aboard the Coronagraph spacecraft triggered a chain reaction that led to the progressive loss of attitude control. In the language of spacecraft engineering, attitude refers not to a satellite's mood, but to its orientation. which way it is pointing, how it is positioned relative to the sun, Earth, and stars. Attitude control is fundamental to everything a spacecraft does. It determines whether the solar panels face the sun, whether the instruments point where they need to point, whether the radio antenna can reach the ground. Lose attitude control, and you lose everything else along with it. As the coronagraph lost its sense of direction in space, its solar panels drifted away from the sun. Without sunlight, the panels stopped generating power. The onboard battery began to discharge. Engineers watching telemetry data from the ground would have seen the numbers dropping, voltage falling, systems drawing down reserves that were never designed to sustain the spacecraft for long. At some point, the coronagraph crossed a threshold. It entered what engineers call survival mode. Survival mode is both a last resort and a lifeline. When a spacecraft's power reserves fall critically low, onboard systems automatically shed every non-essential function, cutting power to instruments, heaters, communication systems, and anything else that is not strictly necessary for basic survival. The satellite goes silent. It stops transmitting. It stops responding to commands. From the perspective of mission control, it disappears. The only goal in survival mode is to preserve enough power and thermal stability to give the spacecraft a chance of recovering once conditions change, if conditions change. Right now, the coronagraph is somewhere in its orbit, drifting in an unknown orientation, unreachable by radio. Whether it is slowly tumbling or has settled into some stable attitude by chance, no one can say for certain. Whether its batteries have enough charge left to wake the spacecraft back up when power returns, no one knows. Whether the anomaly that started this cascade has caused any permanent damage to onboard systems, that is also unknown. The spacecraft that was supposed to show us the sun's corona in extraordinary detail has become, for now, a mystery itself. But the Proba 3 has something most space missions do not. It has a companion. The Occulter spacecraft, the second half of this remarkable two-satellite system, is healthy and operational. It is still flying, still communicating with the ground, still functioning exactly as designed. And mission teams at ESA are now exploring something audacious, using the Occulter to help find and potentially rescue its partner. The idea being investigated is to maneuver the Occulter into a position where it can visually observe the coronagraph, essentially using one spacecraft as a remote observer of the other, and determine the coronagraph's orientation from a distance. If engineers can figure out which way the drifting spacecraft is pointing, they can calculate when and whether its solar panels might naturally rotate back toward the sun, and whether there is any opportunity to re-establish contact. It's a recovery scenario that has no real precedent. The two Proba 3 satellites were designed to fly in formation to study the sun, not to perform search and rescue operations on each other. The precision required to safely approach a spacecraft that is not cooperating, that is not maintaining its position, that may be rotating unpredictably, that is an extraordinary challenge. But ESA's teams are not without resources. The same formation flying technology that made Proba 3's science possible might now be what saves it. There is no guarantee this story has a happy ending. Space is unforgiving in ways that are difficult to fully appreciate from the surface of a planet that has abundant air, gravity, and the option to stop and think. Up there, problems compound. Systems that fail can take others with them. A spacecraft in survival mode may wake up, or it may not. The investigation into the root cause of the anomaly continues, and until engineers understand what triggered the chain reaction in the first place, they can't fully assess what the path forward looks like. What is already certain is that even in its current troubled state, Proba 3 has already changed what we thought was possible. Formation flying at this level of precision had never been demonstrated before. The artificial eclipse technique it pioneered opens a door that cannot be closed. Future missions will build on what Proba 3 proved can be done. The science data already collected represents a genuine leap in our understanding of the solar corona. None of that disappears because one spacecraft is currently in trouble. There is something quietly profound about a machine designed to watch the sun now sitting in darkness, waiting for light to return. Somewhere above us, the coronagraph is drifting through the void, patient, silent, built by human hands and sent on a mission of extraordinary ambition. Whether it wakes up or not, the story of Proba 3 is already one worth telling. A story about how far we'll go to understand the star that makes all life on Earth possible, and what it costs when something goes wrong 90 million miles from home.